In the previous video, we introduced the notion of a Maclaurin series, which was a way to take a function and represent it as a power series, which is something a little bit like a polynomial. So let's first recall what that formula said. We started with the function f, and we said that f has a Maclaurin series if f of x is equal to an infinite sum of terms of the form take n derivatives of the function f, plug in 0, this gives us a number, divide that by the number n factorial, and then put an x to the n next to it. So this is a power series, and if the function f of x equals this power series, then we say that f has a Maclaurin series. There's a related concept called a Taylor series. And a Taylor series is exactly like a Maclaurin series, except you can use any value of x, not just the value 0. So there's a Taylor series at the value x equals a. And so we say a function has a Taylor series at a if we can write f of x as an infinite sum once again. And here, what we're going to do is we're going to take all the instances of 0 in this formula and replace them with a's. So the obvious one is this 0 here. So we take n derivatives, and instead of plugging in x equals 0, we plug in x equals a. We still divide by n factorial. And then the only slightly tricky part is that this x raised to the power n we have to think of as x minus 0. So this becomes x minus a raised to the power n. It's important to remember this minus sign here, which doesn't appear in the Maclaurin series formula. Now, we're going to compute some examples of these, and we're just going to stick to the case of Maclaurin series, and it's only because it's easier to do, not because there's some fundamental difference between a Taylor series and a Maclaurin series. So what kinds of functions have Maclaurin series, and what do they look like? First of all, any polynomial has a Maclaurin series and a Taylor series at any value of x equals a. And what is that series? It's just the same polynomial that you started with. That's not a particularly complicated example. So perhaps the most useful kind of first example of a non-trivial Maclaurin series is the function f of x equals e to the x. So what we have to do to compute the Maclaurin series is we have to take derivatives, and we have to plug in x equals 0, and then we'll just apply our formula. Now, the exponential function has the special property that when we take its derivative, we get back exactly the same function. So that means the value of the derivative at 0 is the same as the value of the function at 0, and that'll be the same as the value of the second derivative at 0 or the third derivative, because they're all the same function. So if we plug in 0, we get e to the 0, and any number raised to the 0 power is 1. So what this says is that the Maclaurin series for the exponential function is the sum of 1 over n factorial times x to the n. So this is the Maclaurin series for the exponential function. You can do a similar thing. If you'd like to compute the Maclaurin series for something like a trig function, sine or cosine is particularly easy. Not quite as easy as this, but there's a repeating pattern of the derivatives for sine and cosine, and you can use that to determine all of these coefficients without very much trouble. Let's do another example that we can do without very much trouble. And that's the function f of x is 1 over 1 plus x. Now, if we did the function 1 over x instead, then that's not even defined at x equals 0. So there's no way the function 1 over x can have a Maclaurin series. But the function 1 over 1 plus x does have a Maclaurin series. So let's see what happens. We need to plug in 0, and we get 1 over 1 plus 0, which is equal to 1. All right. Now we need to start taking derivatives. And to take the derivative of this, I'm going to think of this as the function 1 plus x all raised to the minus 1. So the derivative will be minus 1 times 1 plus x to the minus 2. And then secretly, there's a times the derivative on the inside, but the derivative on the inside is 1. So we don't have to do anything. If I plug in 0 here, you can see that this will be 1 plus 0 to the minus 2. So that's 1 over 1 plus 0 squared. So that's still going to be 1. And we just get a minus 1. What about the second derivative? Well, there's a minus 1 times minus 2 times 1 plus x to the minus 3. So you can see then that the second derivative at 0 is just minus 1 times minus 2, which is 2. We'll do one last example, which is the third derivative. And it's minus 1 times minus 2 times minus 3 times 1 plus x to the minus 4. So hopefully you can see the pattern emerging. We always get something where when we plug in 0, it becomes 1. And then we've got minus 1 times minus 2 times minus 3. And this 3 is the same as the number of derivatives that we've taken. So this becomes minus 6. So taking these numbers, these look a lot like n factorials with minus signs, with 1 derivative, with 3 derivatives. If you carried on, you'd find another minus sign at 5 derivatives. So this says that the Maclaurin series for 1 over 1 plus x is the sum from n equals 0 to infinity. And then we have these terms here, which are n factorials. And then it's a times a minus 1 to the number of derivatives. So at 1 derivative, there's a minus 1. At 2 derivatives, we had 2 minus signs. So that would be minus 1 squared, and they both cancel. We always divide by n factorial, and then times x to the n. In other words, this is the sum of minus 1 to the n times x to the n. So if we write out the first few terms, the term for n equals 0 becomes 1. The term for n equals 1 becomes minus 1 to the 1 times x. So that's minus x, and then it'll be plus x squared minus x cubed, and so on. We can modify this example very slightly to, instead of being 1 over 1 plus x, let's take 1 over 1 minus x, and that'll get rid of all of these minus signs here. So this was 1 over 1 plus x. And if we do 1 over 1 minus x, this becomes just the sum of the x to the n's. And this formula you've probably seen before as the formula for the sum of a geometric series. This is precisely what we have here, a geometric series. And the answer, when you sum from n equals 0 to infinity, is just 1 over 1 minus x. Now this is a great example because this shows, these two functions show that, first of all, if you compute your Taylor series or your Maclaurin series, it might only work for some values. So you can see from this formula that if we plug in x equals 1, something bad is going to happen because it will be 1 divided by 0. And it's important to point out that it might not work at all. There is the example of the function 1 over x, which is not defined at x equals 0, and so can't have a Maclaurin series. But you can even have more complicated functions where you could generate an answer, but it'll actually be the wrong answer. Now, it's very complicated to come up with those. So in practice, usually, as long as you can compute all the derivatives and plug into this formula, then you will have a Taylor or a Maclaurin series.